What is the nature of the round-off error here? Can someone help me unpack what exactly is going on under the hood here? I'm on 64-bit Python 2.7. For the first, I would assume that since there is only a precision of 15 for float that it's just round-off error. The true floating point answer might be something like, and the decimal just gets locked of. But the second result makes me question this understanding, and can't one be represented exactly? Any thoughts? Edit, just to clarify. I'm not in any way suggesting that the answers are wrong. Clearly, they're right, because, well, they are. I'm just trying to understand why.
It's just rounding as close as it can. 1e16 in floating hex is 0 by 4341 C37937E08000. 1e16 plus 2 is 0 by 4341 C37937E08001. At this level of magnitude, the smallest difference in precision that you can represent is 2. Adding 1.0 exactly rounds down, because typically IEEE floating point math will round to an even number. Adding values larger than 1.0 will round up to the next representable value.
Ten to the power of 16 equals 0 by 002386 F26 FC10000 is exactly representable as a double precision floating point number. The next representable number is 1e16 plus 2. 1e16 plus 1 is correctly rounded to 1e16, and 1e16 plus 1.1 is correctly rounded to 1e16 plus 2. Check the output of this C program. Output.
Let's decode some floats, and see what's actually going on. I'm going to use common list, which has a handy function for getting at the significand, aka mantissa, and exponent of a floating point number without needing to twiddle any bits. All floats used are IEEE double precision floats. That is, if we consider the value stored in the significand as an integer, it is the maximum power of 2 available. 4,503,599,627,370,496 equals 2 to the power of 52, scaled down. 2 to the power of minus 52. Isn't stored as 1 with an exponent of 0 because it's simpler for the significand to never have zeros on the left, and this allows us to skip representing the leftmost 1 bit and have more precision. Numbers not in this form are called denormal. Let's look at 1e16. Here we have the representation, 5 quadrillion, 2 to the power of 1. Note that the significand, despite being a nice round decimal number, is not a power of 2. This is because 1e16 is not a power of 2. Every time you multiply by 10, you are multiplying by 2 and 5. Multiplying by 2 is just incrementing the exponent, but multiplying by 5 is an actual multiplication, and here we've multiplied by 5 16 times. Observe that this is a 53-bit binary number, as it should be since double floats have a 53-bit significand. But the key to understanding the situation is that the exponent is 1. The exponent being small is an indication that we are getting close to the limits of precision. This means that the float value is 2 to the power of 1 equals 2 times this significand. Now, what happens when we try to represent adding 1 to this number? Well, we need to represent 1 at the same scale. But the smallest change we can make in this number is exactly 2, because the least significant bit of the significand has value 2. That is, if we increment the significand, making the smallest possible change, we get. And when we apply the exponent, we get 2 times 5 quadrillion 1 equals 10 quadrillion 2, which is exactly the value you observed. You can only have either 10 quadrillion or 10 quadrillion 2, and 10 quadrillion 1.1 is closer to the latter. Note that the issue here isn't even that decimal numbers aren't exact in binary. There's no binary repeating decimals here, and there's plenty of 0 bits on the right end of the significand. It's just that your input neatly falls just beyond the lowest bit.
With NumPy, you can see the next larger and smaller representable IEEE floating point number. So, and therefore 1e16 plus 1.1 is correctly rounded to the next larger IEEE representable number of 10 quadrillion and 2.0, as is. And 1e16 something slightly larger than 1 is rounded down by 2 to the next smaller IEEE number. Keep in mind that 32-bit versus 64-bit Python is irrelevant. It is the size of the IEEE format used that matters. Also keep in mind that the larger the magnitude of the number, the epsilon value, the spread between the two next larger and smaller IEEE values basically changes. You can see this in bits as well.
If you want those more, please consider subscribing.